Okay, so I want to summarize what we did last time. And basically what we did last time was prove that the script M is a sigma algebra. So the next task, the next thing we want to do is prove that if B is the Borel sigma algebra, then B is a subset of script M. Okay, so to do this, well, it's enough to show that each open interval A to B is in script M for A less than B. Okay, and the reason is basically the logic we've been employing many times in the videos and in the homework. Well, this script B, well, if we can do this, if we can do what I'm putting in red, so to clarify, if we can show this for every open interval A to B, then what we'll have is we'll have a sigma algebra script M containing all open intervals. Script B is the smallest such sigma algebra, and henceforth, script B as the smallest such sigma algebra will be a subset of script M. So that has a practical meaning that every open interval and really every open set is measurable. So script M will be a sigma algebra containing all open sets. Remember, the homework is that the sigma algebra generated by open intervals A to B is the sigma algebra generated by open sets. Okay. Right. Right, Borel. And again, just in case there's any confusion from what the book does, the book defines the Borel sigma algebra as the sigma algebra generated by open sets. I define it as the sigma algebra generated by open finite intervals. But the homework is that they're the same. They're literally the same class of subsets of R. So they're literally exactly the same. So they're, so yeah, they're equal. They're the same. Doesn't matter how I define it, one or the other, my definition or the book's definition, you get the exact same thing. Okay. And right, so to clarify, A and B are both real numbers. Neither of them are infinity or minus infinity. Okay, so so actually, it's enough to show that every set of the form A to infinity is in script M. Okay, and basically, we did this in the synchronous office hours, but I'll just go over it. I think we did. If we didn't, it doesn't matter if we did or didn't, because I'll go over it again right now. Okay. So this here is really my task. And what I'm claiming is that if I can prove this here, then I will have what's in the red. I will have that every finite open interval is in script M. Okay. Why does what's in the black imply what's in the red? Well, the answer is very simple. Well, So from what's in the black, I want to show that every interval minus infinity to b can be written in terms of these kind of intervals in the black. And we can do that very easily. Or not so much, well, yeah, we want to write it in terms of these kind of intervals a to infinity. Well, right, so this here is going to be the complement of, and here b is something, some real number. So this is going to be b to infinity complement, which can be written as this intersection here, b minus 1 over n, the complement here, and this here, right, so we're assuming that, I'll use a different color. So if I can show this, so let's give this a name. Let's call this star here. So if star is true, then each one of these is an m. Hence the intersection, the countable intersection is an m. Hence the complement is an m. So this is an m. And yeah, I do think I'm repeating almost like precisely what I did in the synchronous office hours, but that's okay. That's all right. Right, so what's the point here? The point here is if this is true, then this is in script m minus infinity to b, and we can write open intervals a to b as minus infinity to b intersect a to infinity, and this will be in script m if this is in script m, and so is this here. If both of these are in script m, then so will the intersection. So that proves that the star here in green implies what's in the red. Okay, so my task is to prove this here. And it's a bit of, it's not the shortest proof ever, but it's not that long. It's really not that bad. All right, so to do this, I need a proposition, which the book, I think, proves this a little later. I think it's worthwhile to just get this out of the way because it's such a quick little proposition here. So the proposition is as follows. Let's say I have any set, subset A of the real line that has measure 0. So let's say A has measure 0, meaning the outer measure of A is 0. Then I claim that for any set B whatsoever, I can excise, I can remove A from B, and the outer measure is unchanged. Which makes sense. I mean, if I'm removing a set that really has no size, then that should not affect the size of B. And that's what exactly I'm saying here. And the proof, I mean, I could give this for homework, but there's just so much homework I really could give. So yeah, I might as well do it as a very simple exercise and playing around with outer measure. So one direction is kind of trivial in the sense that certainly B take away A is a subset of B. So let's use the monotonicity property, which says that whenever I have something as a subset of something else, the outer measure of the possibly smaller set is less than or equal to the outer measure of the possibly larger set. Okay. So that proves essentially half of this. The other half is not much harder. Let's use finite sub additivity. Okay? So I want to emphasize we don't know that A and B are measurable. They're just any subsets of the real line. Okay? So we can write B as B take away A, disjoint union A. So it doesn't matter that this is a disjoint union. We don't know, we don't know if anything is measurable. So all we can use is finite sub additivity. Okay. So remember, if we don't know anything is measurable, if we're not dealing with measurable sets, you really, all you have is sub additivity. But that's all we need. So it's B take away A plus M star of A. So now we're finally going to use the fact that this here has measure 0. That's our assumption. Certainly this here is true without any assumption on A and B. So we got to use measure 0 somewhere, and this is where we use it. So this is going to be equal to M star of B take away A. So, right, M star of B take away A is less than or equal to M star of B. M star of B take away A is bigger or equal to M star of B, so they're the same. They're equal. So again, basically like a little exercise in playing around with the basic properties of outer measure. Okay, so right, let's get down to business here. And let's prove, I believe I used the screen here. Let's prove star, which is this here. All right. Okay, so the proof is as follows. So remember what we need to prove. Just remind you of what we need to prove. Let's say we have an A as a subset of R. So remember we need to prove that M star of A is bigger or equal to, A is arbitrary. We need to show that's bigger or equal to A intersect little a to infinity plus M star of A intersect A to infinity complement. That's what our task is. Okay. So yeah, I'm going to erase this here because this is what we need to prove. Okay. So I'm going to work kind of backwards and manipulate these two here. Okay. So let me get rid of this. So write it down if it'll help you kind of keep track of the goal of everything. So this here, so let me just move this down here because it looks a little nicer. Little dumb things like that annoy me, but anyway. Okay, so this here, the right-hand side of what we need to look at, well, this is going to be equal to, obviously, A infinity complement is minus infinity to B closed. Okay, so this is going to be, whoops, I don't know why I put B, it's A. Strange, sorry about that. Okay, so I'll just rewrite this, what I just basically wrote. Now I'm going to use a property after I write this that I can excise a set of zero measure. So anything countably infinite has zero measure. So certainly anything finite has zero measure. In particular, one single point has zero measure. So this doesn't change here, m star of a intersect a to infinity. But here I'm excising the point A to get A intersect minus infinity to A open. And it has the same outer measure. And again, I'm just using the fact that a single point has zero measure. Yeah, so I'm using the fact that a single point has zero measure, so I can excise a single point. So maybe A's and B's are unfortunate notation, but hopefully it doesn't. Yeah, I mean, if anything, I can change it to X's and Y's, but maybe it's a little clearer. Maybe it's, anyway, I won't do that. But anyway. All right, so let's call this star star. And there's a reason why I don't want closed A here. I want open A. Okay, right, so what I need to prove is, well, remember, I need to prove that this whole thing here is less than or equal to outer measure of A. Well, this whole thing here is equal to double star star, so I need to prove that double star star is less than or equal to the outer measure of A. So that's my task here. Okay. Right. 1 second. So actually, let me call this M rather than double star star. Okay, so without loss of generality, I can assume that M is strictly between 0 and infinity. Why is that? Well, if M is infinity, then one of these two has to be infinity. And A is larger than one of these two sets, so the outer measure of A also has to be infinity. So this is trivially true. On the other hand, if M is 0, then basically what we kind of did here gives you that basically because M star of A is less than or equal to this sum here, and the only way M is 0 is if both of these are 0, and hence this here is 0, then that means the outer measure of A has to be 0. Okay. So basically, if M is either 0 or infinity, then this is trivially true. Okay. And if I went a little fast doing that, definitely you should check yourself that this here is true, what we need to show if M is 0 or m is infinity. Okay, so right. So the following I'll leave for actual homework that I probably will collect. It's almost a definition of outer measure. Basically, it's a definition, really just the infimum definition. So we have outer measure of A is bigger or equal to m for any positive real number m, if and only if for any countable cover of A by intervals, so I should put cover here, well, we have that the sum of the lengths is bigger or equal to m. Okay. So this has to be true for every single countable cover of A. Okay. All right, so now, and I should mention, like always, I'm following Royden's proof, but just filling in a little bit more detail. All right, so yeah, following Royden's proof, let's explain why we want to excise A from this set here and maintain the same outer measure. Well, the reason is basically because the intersection of two open intervals is again an open interval, and that's very important for this proof. So let's define, following the book's notation, ik prime to be AK, BK intersect A to infinity. So AK, BK is just any cover of A. So what we have to do is show that the sum of the lengths of this arbitrary cover of A by these countable open intervals, this sums up to be bigger or equal to m. That's our task to finally finish up this proof. Okay. Okay, and let's define ik second prime to be ak bk intersect minus infinity to a. Okay. So I claim that both are intervals and, well, the length of AK to BK is going to be the length, script L for length, of IK prime plus the length of IK second prime. So I'm not going to rigorously prove it, but I'll basically tell you how to rigorously prove it. Pictorially, this is pretty obvious. Well, let's look at multiple cases and just kind of see what's going on. And as I said, really, what I'm going to do pictorially tells you how to prove it. And if you so desire to, you can do that. Well, let's look at 3 cases. The first case is A is between AK and BK. So either A is between AK and BK strictly, or it's not. Sure, we'll all agree on that. So in this case, I don't think I'll fit this all in one line, but we'll see. It's a little bigger. Okay, so let's say we have AK, we have BK, and sitting somewhere in between is A. Okay, so right, so in this case, what is IK prime and IK second prime? Well, IK prime is just this interval intersect A to infinity. So this is just IK prime. And IK second prime is the interval intersect minus infinity to A, everything less than A. So that's just going to be the left half, or the left portion of what I had. Pardon me for a second. Sorry about that. So IK second prime is this interval intersect minus infinity to A. So clearly in this case, you can see that BK minus AK, the sum, not the sum of anything, the length of AK to BK is certainly the length of these two intervals, because the length of these two intervals is just BK minus A plus A minus AK, which gives you BK minus AK. And the other cases are even easier. Well, if A is not in this interval, then either A is less than or equal to AK. Let's do that case. Or A is bigger or equal to BK. So basically, this is a proof. I shouldn't say this really isn't a proof. I just proved this in case 1. And I'm basically going to prove it in case 2. So here, let's say we have A, and let's say we have AK, BK. So I should emphasize, certainly A could be equal to AK, doesn't matter. So in this case, we have, this is IK prime. Again, IK prime is AK BK intersect A to infinity. And IK second prime is empty. So right, so the sum, the length of IK prime is BK minus AK. The length of IK double prime is 0. Third case is basically the same. Let's say in this case, B is bigger or equal to BK. So again, B could be BK. There's no problem with that. Just for graphical purposes, I'll draw it bigger. So this is AK, BK. I don't feel like erasing. So this here is, well, now this is IK Sorry, I don't know why I put B. This should be A. I don't know where B came from. Sorry about that. There is no B anywhere. Just looking at A, AK, and BK. Okay. Right. So here, IK prime. This one right here is empty. So the length of IK prime is 0. The length of IK second prime equals the length of AK to BK because I second prime is AK to BK. Same thing here. IK prime is AK to BK. So anyway, just get, yeah. So this is true. All right. So yeah, all the hard work has been done, really. Let's just kind of finish up. So A is covered by these intervals. So A is a subset of the union of these intervals, AK to BK. So A is a subset of this union here. Well, just intersect this with A to infinity. Little a to infinity. So this is a subset of using just basic introduction to proof stuff. BK intersect A to infinity. And so remember, this is IK prime. By definition, that's how we defined it. And let's give this a name too. Let's call this A1. Right, do the same thing, but from minus infinity to A. This is a subset of same thing, but with minus infinity to A. AK, BK intersect minus infinity to A, which again is IK second prime. So this proof, I have to admit, is a bit annoying because there's a lot of like different sets floating around. Got to be mindful of what each one is. But otherwise, the proof is not too bad. Let's give this a name A2. Okay, so right, so these are open intervals. These are open intervals that cover respectively big A1 and big A2. So we can use the definition of outer measure as an infimum. So by nothing but the exact literal definition of outer measure, it's the infimum of all possible sums, countable sums of lengths of covers of A1. Well, this is one of them. So this sum of lengths of covers of A1 is bigger or equal to the infimum. The infimum is a lower bound. And we also have same thing for A2. The outer measure of A2 by the infimum definition is less than or equal to the sum of these, the sum of the lengths of these intervals. Okay. Okay, so right. So remember, actually, what we're trying to prove. So M here, so we called this, we just defined this as A1, and we just defined this as A2. Okay. Let me make sure I get my A1s and A2s. Yeah. Okay. So M, big M, is the sum of M star of A1 and M star of A2. So we need to prove that the sum of M star of A1 and M star of A2 is less than or equal to the outer measure of A. Okay, that's what we need to do. Okay, so yeah, just kind of reiterate, write down what I basically said. Finally, we have M equals, we set M to be this here. So this here is less than or equal to, we'll just combine this together. K equals 1 to infinity, ik prime, k equals 1 to infinity. Make that a little better looking. Well, that's just going to be equal to pull everything into one sum. As always, these are, non-negative quantities, so convergence is not an issue really. It either converges to a real number or positive infinity. Right, okay, so now let's use this fact here. I'm going to put this in orange. So the sum of these two lengths is bk minus ak. Yeah, I'll leave this in orange actually, because that's exactly what I'm doing. Or maybe I'll do it like this. So this is going to be the sum, k equals 1 to infinity, bk minus ak and right, so that's exactly what we need to do. We needed to show that if we start off with a countable cover of A, that we have this being true. Okay. So we start off with a countable cover of open intervals of A, and we need to show that this is true, and this is exactly what we did. We showed that this sum here is bigger or equal to M. So that proves it. So a lot of reductions, but so yeah, maybe take some time to digest this. And all right, so yeah, so I want to do one more little proposition, and then I'll basically summarize everything we've done so far, basically from the start of, well, I mean, the sort of second start of the course, if you will. Yeah, it's a little bit strange that the book basically proves this proposition that I'm going to state and then doesn't really summarize everything. It really proves more properties of outer measure and then summarizes things, which I think is bizarre. I think it's a good place to summarize after what I prove is true. So I have a little proposition here, and that's just that translating a measurable set doesn't affect the fact that it's measurable. So if E is measurable, then E plus X, and just to remind you, that's just a set of all E plus X, where E is in big E, then that's also in M. And it's just an easy, really an easy proof. So let's say A is a subset of R. Okay, so usually we have to prove that this is right. So usually what do we need to do? We need to prove that this is going to be bigger or equal to A intersect E plus X plus outer measure of A intersect E plus X complement. That's what we usually need to prove. Well, it's more clear to actually just directly prove equality. And certainly that's a definition of measurability of E plus X. And to prove that, it's usually enough, well, it's always enough to just prove basically the hard half of it, which is bigger or equal to. But yeah, it's more clear to just directly prove that these are equal. And I'm going to do that by focusing on the left-hand side. Okay, so let's get rid of all this and let's prove this. Okay, so this is going to be equal to, well, we proved that outer measure is translation invariant. So I'm going to subtract X here. And when I say minus X, X, of course, is a real number. Well, it has the obvious meaning. Just this here. I mean, that's what A minus X is. It's really like A plus minus X. So let me make this plus again. Okay, so now I can use the fact that E is measurable. So the fact that E is measurable gives me that this is going to be A minus X intersect E A minus X intersect E complement. Okay. So that's just from E being measurable. Right, so I want to use translation invariance one more time of outer measure. So I can add X to both of these sets. So this is going to be, I'm going to need some room here. So I want to move this over. So this is going to be A minus X intersect E. The whole thing plus X. So I probably should put another bracket here, but what I mean is really this whole thing here plus X. And do the same thing, A minus X intersect E complement, whole thing plus X. So maybe I'll do one more bracket here in blue. Okay, so right, so what do I want to do now? I want to use just a simple fact from 299 that it's not necessarily immediately obvious, but you can prove it very easily. So I claim that this is going to be equal to, and I'll explain this in a moment, A intersect E plus X, A intersect E plus X complement. And that's exactly what I wanted to prove. And sorry, that does not look like a plus sign, and that barely looks like a plus sign. Okay, right. Remember, that's exactly what we wanted to prove. That proves that E plus X is measurable. So where does this come from? Well, here I'm just using the fact, and again, this is not obvious, but you can prove it, that A minus X intersect E plus X is going to be equal to A intersect E plus X. And I'll give this as a homework. I don't think I'll collect it. But yeah, that's exactly what I'm doing here. I'm saying that these two sets are equal and these two sets are equal. So, whoops. A minus X intersect E complement plus X is going to be equal to A intersect E plus X complement. And that's the proof. That's exactly what I needed to do to show that E plus X is measurable. Okay, so right, so let me do a new screen share for a moment. So before I summarize, yeah, so this is a proof I just did, proposition 10. And I also proved proposition 8. So yeah, I guess I'm going to summarize theorem 9, but I also want to just quickly skip ahead to basically theorem 14, which is just a summary of everything we've done. Okay. So right, so let me do that. Because I think it's worthwhile to summarize everything we've done so far. So a summary is following. So let's define Lebesgue measure So I mentioned this before, I think the first video. So this is called Lebesgue measure. Well, as I mentioned, it's nothing mysterious. It's literally just outer measure restricted to script m. So this is little m. Okay, 1, script m. And I'm being redundant, I know. Maybe I'm being annoying, but I really just think it's good to summarize everything. Because we put a lot of work into this, so let's kind of summarize all the work we've done. This is a sigma algebra containing all open subsets of R. Okay. So I'm not going to reiterate exactly what this means, but as I've mentioned multiple times, this means, as I've hopefully convinced you through examples and the definition of a sigma algebra containing all open sets, the script M contains every single possible subset of the real line that you can probably ever imagine using in any future mathematical endeavor that you partake in. 2, and remember that surprisingly, this was probably the hardest thing we did. In my opinion, this was the hardest thing we did. For any interval I, any interval is measurable by basically 1 here. So I'm justified in using M, not necessarily outer measure. Well, the two are the same when we're dealing with a measurable set, but I is measurable. We've proven that. Well, this is just the length of the interval I, the unambiguously defined length of I. 3, and I should mention also here that translates of stuff in script M are also in script M. So it's a little messy, but all I'm saying here is that translates sets of the form E plus X for E measurable are also measurable. I mean, every now and then in analysis, you have to move sets around. So it's very important to know that. Sorry, I have my screen's a little dirty, so I have something here, and I thought that was something I wrote. But anyway. Okay, 3. We actually proved quite a bit more, but this is really what you want and care about. If EK are measurable, then we know the disjoint union is measurable. Any countable union of measurable sets is measurable. Well, this is just going to be the sum of the measure, the Lebesgue measure of EK. And this is if each EK is in script M. Okay, so what I want to do next is prove some further important but more, I guess, exotic. I wish exotic is not the right word. Maybe less intuitive properties of Lebesgue measure that are extremely important for both future math and the prelim. But yeah, that's what I'm going to do in the next video. I think this is a good time, good place to end. And I'll put new homework up today. So do get the old homework in soon. I'm pretty lenient when I get homework in. So please get it in soon. All right, so long. Take care. Bye-bye.